Imagine standing in a room where everything you can see, the furniture, the walls, the ceiling, makes up less than 15% of what's actually there. The rest, 85% of the room, is invisible. Not hidden behind curtains or tucked into corners, but fundamentally imperceptible. You can feel its presence. You know it must be there because the visible objects behave as if they're anchored to something, held in place by an architecture you cannot see. This is not science fiction. This is our universe. Hello and welcome to the Sleepy Astronomer. Tonight, we're drifting into one of the most profound mysteries in all of science: dark matter, the invisible scaffolding that holds galaxies together, shapes the structure of the cosmos, and outweighs everything we can see by a factor of more than 5 to 1. A substance so elusive we've never directly touched a single particle of it, yet so essential that without it, stars would never have formed, galaxies would fly apart, and none of us would be here to wonder about it. If you're settling in for the first time, welcome aboard our gentle journey through the cosmos. And if you've travelled with me before to explore the quiet wonders of space, it's wonderful to have you back among the stars. Whether you're tucked into bed, curled up on a favourite chair, or perhaps lying back where you can see the night sky through a window, I'm so glad you're here. Our journey begins in the 1930s with a Swiss astronomer studying clusters of galaxies, following a trail of mathematical breadcrumbs that leads to one of the most extraordinary revelations in the history of science. Pure calculation pointed the way to an invisible universe, and decades of observation confirmed what the numbers had already whispered into the darkness. Beyond the comfortable realm of what we can see and touch, reality extends into territories that exist more in the language of mathematics than in the familiar world of light and colour. There's something deeply humbling about discovering that most of the universe is hidden from us. Ancient philosophers wondered what lay beyond human perception: Plato's shadows on the cave wall, the invisible realms of spirit and essence. Modern cosmology has found its own invisible kingdom, stranger and more substantial than any myth. Dark matter permeates everything, forming halos around galaxies, weaving the cosmic web that connects one cluster of galaxies to another across billions of light years. It was here before the first stars ignited, providing the gravitational wells into which ordinary matter fell and condensed. Every galaxy, including our own Milky Way, sits cradled in a vast sphere of invisible mass, like a visible flame suspended in an invisible lantern. Only one thing has ever allowed us to glimpse this hidden realm: gravity. Dark matter doesn't emit light, doesn't absorb it, doesn't interact with it in any way we can detect, but it pulls, it bends space, shepherds galaxies, and leaves fingerprints in the cosmic microwave background radiation that whispers to us from the edge of the observable universe. Through these gravitational whispers, we've learned to read the invisible. From the puzzle of galaxies spinning too fast to the cosmic web mapped by modern supercomputers, dark matter reminds us that the universe still holds wonders beyond our direct experience. Some things are too elusive to see, too ethereal to touch, yet real enough to hold galaxies together, and patient enough to have shaped the cosmos for 13 billion years while waiting for curious minds to notice. So, find your most comfortable position. Whether you're curled up in bed, settled on the sofa, or perhaps lying back in a chair where you can see the stars through a window, stars held in their galactic homes by invisible hands. Take a deep breath, and let's begin our gentle drift into the hidden universe, past what our eyes can see, beyond the reach of our most powerful telescopes, into the realm where mathematics becomes our only guide. Out there, in the vast darkness between visible things, dark matter waits, patient, invisible, and beautiful, ready to reveal how little we truly see of everything that is. In 1933, a Swiss astronomer named Fritz Zwicky was doing something that seems, on the surface, rather mundane. He was watching galaxies. Not individual stars, mind you, but entire galaxies. Those vast islands of hundreds of billions of stars, each one a complete universe unto itself. Zwicky was watching how these galaxies moved within a cluster, a cosmic neighborhood where hundreds of galaxies drift together through space, bound by their mutual gravitational pull. He was looking at the Coma Cluster, a collection of over 1,000 galaxies about 300 million light-years away from us. At that distance, even the largest galaxies appear as nothing more than faint smudges of light, fuzzy patches barely distinguishable from the background glow of the universe. But Zwicky wasn't interested in what these galaxies looked like. He wanted to know how fast they were moving. This is where things get interesting. You see, there's a beautiful relationship in physics, a kind of cosmic accounting that governs how objects move when they're bound together by gravity. It's called the virial theorem, and it's elegantly simple in what it tells us. If you know how fast things are moving in a gravitationally bound system, whether it's planets around a star or galaxies in a cluster, you can calculate how much mass must be present to keep everything from flying apart. Think of it like a dance. Imagine dancers holding hands, spinning in a circle. The faster they spin, the harder they have to grip each other's hands to stay connected. If they're spinning very fast, they need to be either very strong or very heavy to maintain their circle. Let go, and centrifugal force would send them flying outward into the crowd. Galaxies in a cluster are engaged in their own cosmic dance, held together not by clasped hands but by the invisible threads of gravity. Zwicky measured the speeds of galaxies in the Coma Cluster by looking at how their light was shifted, stretched toward redder wavelengths if they were moving away, compressed toward bluer wavelengths if they were moving toward us. This is the Doppler effect, the same phenomenon that makes an ambulance siren drop in pitch as it passes you on the street. By measuring these shifts, he could determine how fast each galaxy was moving through the cluster. And then he did the math. He calculated how much mass would be needed to keep galaxies moving at those speeds from escaping into intergalactic space. The answer should have been straightforward. Add up all the visible matter in all those galaxies, the stars, the glowing gas, everything that emits light, and that total mass should roughly match what the virial theorem predicted. It didn't, not even close. The galaxies were moving far too fast. According to Zwicky's calculations, they should have escaped the cluster's gravitational pull billions of years ago, scattered into the depths of space like sparks from a fire drifting up into a dark sky. Yet there they were, still bound together, still dancing their slow cosmic waltz. Something was holding them together, something with mass, enormous amounts of mass. But whatever it wasn't shining. It wasn't emitting any light that Zwicky's telescopes could detect. The discrepancy wasn't small. Zwicky found that the cluster needed about 400 times more mass than what he could see to keep the galaxies bound together. 400 times. Imagine looking at a person and being told that for every pound of flesh and bone you can see, there are 400 pounds of invisible something surrounding them, permeating them, holding them together in ways you cannot perceive. It's absurd. It defies common sense. Zwicky called this missing mass dunkle materie, dark matter, The name was descriptive, not poetic. It was dark because it didn't shine. It was matter because it had to have mass to exert gravitational force. That was all he knew. He didn't know what it was made of, where it came from, or why it didn't interact with light. He just knew it had to be there, lurking in the spaces between galaxies, invisible yet essential. The scientific community's response to Zwicky's discovery was, let's call it, underwhelming. Many astronomers simply dismissed it. Zwicky must have made an error in his calculations, they said, or perhaps his observations were flawed. Maybe the galaxies weren't really moving that fast, or maybe there was some exotic form of regular matter, dim stars, cold gas, dark planets, that he just hadn't accounted for. Surely the problem was with Zwicky's methods, not with our understanding of the universe. To be fair, Zwicky was not an easy person to work with. He was brilliant, yes, but also abrasive, stubborn, and prone to calling his colleagues spherical bastards, a term he invented, which he explained meant people who were bastards no matter which angle you looked at them from. He had a talent for alienating people, which didn't help when he was trying to convince the astronomical establishment that 85% of the universe was invisible. And so, for decades, the problem of the missing mass sat mostly ignored. It was a curious anomaly, yes, but anomalies happen. Instruments malfunction, calculations contain errors, and sometimes the simplest explanation is that someone made a mistake. The universe, after all, had behaved quite reasonably for centuries. Why would it suddenly reveal itself to be mostly invisible? But then, in the 1970s, another astronomer picked up the thread that Zwicky had left dangling. Her name was Vera Rubin, and she wasn't looking at galaxy clusters. She was looking at individual spiral galaxies, beautiful pinwheel structures like our own Milky Way, with arms of stars curving gracefully outward from a bright central bulge. Rubin wanted to understand how these galaxies rotated. It's a simple question with what should have been a simple answer. Stars in a galaxy orbit around the galactic center, held in their paths by gravity, just as planets orbit the sun. And just as planets farther from the sun move more slowly, Neptune takes nearly 200 years to complete one orbit, while Mercury zips around in just 88 days. Stars farther from a galaxy's center should also move more slowly. This relationship is one of Kepler's laws, a beautiful piece of celestial mechanics that had been verified countless times in our own solar system and in binary star systems. The math is elegant. Orbital velocity should decrease with distance from the center of mass. Plot it on a graph, and you should see a curve that rises sharply near the center and then falls off steadily as you move outward, like a hill that climbs and then descends. Vera Rubin, working with astronomer Kent Ford, measured the rotation speeds of stars at various distances from the centers of spiral galaxies. They used a spectrograph, an instrument that splits light into its component colors and reveals the subtle shifts caused by motion. Night after night, they painstakingly collected data, building up rotation curves for galaxy after galaxy. The curves didn't fall. They stayed flat. Stars at the outer edges of galaxies were moving just as fast as stars closer to the center. Some were even moving faster. It was as if Neptune were orbiting the Sun at the same speed as Mercury, or as if a child on the outer edge of a merry-go-round were somehow keeping pace with a child near the center without being flung off into space. The galaxies were rotating in a way that simply shouldn't have been possible if the only mass present was the mass we could see. The implications were staggering. To keep those outer stars moving so fast without flying off into intergalactic space, there had to be more mass present, much more mass, extending far beyond the visible edge of each galaxy. The stars and glowing gas clouds that we could see were apparently embedded in vast spheres of invisible matter, dark halos that extended perhaps 10 times farther out than the visible disk. And it wasn't just one or two galaxies showing this strange behavior. Every spiral galaxy Rubin and Ford examined showed the same flat rotation curve. This wasn't an anomaly. It was a pattern, a rule. Something fundamental about how galaxies worked. At first, astronomers tried to explain it away with conventional matter. Maybe there were enormous numbers of dim stars lurking in the outer reaches of galaxies, brown dwarfs or red dwarfs too faint for telescopes to detect easily. Maybe there were vast clouds of cold hydrogen gas, or perhaps the halos were filled with stellar remnants, white dwarfs, neutron stars, black holes left over from stars that had lived and died billions of years ago. These explanations had a certain appeal. They didn't require inventing new physics or new forms of matter. They just required that normal matter be hiding in ways we hadn't fully accounted for. And so, for a time, astronomers searched for this hidden normal matter. They looked for it in multiple wavelengths, infrared light that might reveal cool dim stars, radio waves that might betray the presence of cold gas, X-rays that might hint at compact stellar remnants. They found some of these things, yes. There were indeed dim stars and cold gas in the outer parts of galaxies. But when astronomers added it all up, it wasn't nearly enough. Not even close. To explain the rotation curves, you needed roughly 10 times more mass than all the normal matter combined. All the stars, all the gas, all the stellar remnants, everything made of protons, neutrons, and electrons. There was another problem with the normal matter explanation. Normal matter, the stuff that atoms are made of, the matter we're familiar with, interacts with light. It can emit light when heated, absorb light when cool, scatter light as it passes through. This is why we can see stars and gas clouds at all. But the rotation curve suggested that most of the mass in galaxies didn't interact with light in any of these ways. It was gravitationally present, but electromagnetically absent, like a ghost that could move objects but couldn't be photographed. The evidence kept mounting. Other astronomers repeated Rubin's observations and confirmed her results. Theorists worked out detailed models of how galaxies should behave with and without dark matter. The models with dark matter matched observations beautifully. The models without it failed to reproduce what telescopes were seeing. Slowly, reluctantly, the astronomical community began to accept what Zwicky had suggested 40 years earlier. Most of the matter in the universe doesn't shine. It doesn't emit light, doesn't absorb it, doesn't scatter it. It reveals itself only through gravity, through the way it pulls on things we can see, bending their paths and holding them in configurations that would be impossible without its invisible presence. There's something almost philosophical about this realization. For all of human history, we've understood the universe through light. Our eyes evolved to detect it, our telescopes were built to collect it, and our theories were constructed to explain it. Light is how we've mapped the cosmos, from the nearest planets to the most distant galaxies. It's been our primary messenger, carrying information across the void. And then we discovered that most of the universe doesn't participate in that conversation. It doesn't send light signals. It doesn't respond to light that passes through it. From light's perspective, dark matter might as well not exist. But from gravity's perspective, dark matter is the dominant partner, the major player, the foundation upon which everything else is built. It's as if we'd spent our entire lives reading books, only to discover that the shelves holding those books, the building containing the library and the ground beneath it all, are invisible to us. We can see the books floating in space, arranged in orderly rows and stacks, but the structure supporting them remains hidden. We know it must be there because the books aren't falling. but we cannot see it, cannot touch it, cannot understand it, except through the architecture it creates. Zwicky saw it first in the dance of galaxies and clusters. Rubin saw it in the rotation of spiral disks. Both were following the same trail of breadcrumbs, following gravity's whispers to something unseen. And what they found was not a small correction to our understanding, not a minor footnote in the cosmic accounting. What they found was that we'd been looking at the universe backward. The light, the stars, the galaxies, everything we'd been studying for centuries was the minority. The scaffolding, the skeleton, the invisible foundation holding it all together was something else entirely. This is where our story truly begins. In the missing mass of galaxy clusters and the flat rotation curves of spiral galaxies, we glimpse the edges of something vast and hidden. In the next chapter, we'll explore what that hidden structure looks like when we map it across the entire observable universe, a cosmic web of dark matter filaments connecting galaxy clusters like neural pathways in some vast, invisible brain. But for now, rest in the knowledge that the universe is stranger and more mysterious than our eyes alone can reveal, and that sometimes the most important things are the ones we cannot see. If you could step outside the universe and look back at it from some impossible vantage point, what would you see? Not the scattered points of light that appear in telescope images, but the actual distribution of matter across billions of light years. What you'd see would look oddly familiar. Not like a random scattering of galaxies, not like stars sprinkled across velvet, but like something organic, like neural pathways, like the filaments of a vast cosmic mycelium spreading through soil, like a web. This is the cosmic web, and it's one of the most beautiful structures in nature. Galaxies aren't distributed randomly through space. They cluster together along vast filaments of dark matter, cosmic highways hundreds of millions of light years long, connecting dense nodes where galaxy clusters gather like cities along ancient trade routes. Between these filaments lie enormous voids, empty regions where almost nothing exists, cosmic deserts that can span 100 million light-years across. And here's the remarkable thing. The galaxies, the stars, the glowing matter we can see, they're just tracing out a pattern that was drawn billions of years ago by something invisible. Dark matter created this architecture. It laid down the blueprint. The stars simply followed, falling into the gravitational wells that dark matter had already prepared for them, like water flowing into channels carved long before the rain began to fall. We discovered this structure not by looking through telescopes alone, but by combining observations with something that would have seemed like magic to astronomers just a few generations ago: computer simulations. Starting in the 1970s and accelerating through the decades since, cosmologists have been building digital universes inside supercomputers, universes that obey the laws of gravity and expansion just as our real universe does. These simulations start simple. You begin with the early universe, just a few 100,000 years after the Big Bang, when space was filled with an almost perfectly smooth distribution of matter and energy. Almost perfectly smooth, but not quite. There were tiny fluctuations, quantum ripples from the earliest moments of cosmic time, differences in density of just 1 part in 100,000. Hardly worth noticing, you might think. But gravity notices everything. Even the smallest overdensity, a region where matter was just slightly more concentrated than average, has a gravitational pull slightly stronger than its surroundings, and that pull draws in more matter, which increases the pull, which draws in even more matter. It's a feedback loop, a snowball effect that builds over time. The rich get richer, the dense get denser. In the simulations, scientists scatter millions of particles across their digital universe, representing dark matter. They don't need to know exactly what dark matter is made of, not yet. They just need to know how it behaves gravitationally, how it responds to the pull of other dark matter. And then they press play. They let the simulation run forward through cosmic time, watching billions of years unfold in minutes or hours of computation. What happens is extraordinary. The dark matter particles begin to drift toward the slightly denser regions. Slowly at first, almost imperceptibly but gathering momentum. The small fluctuations grow into larger ones. Regions that started just a tiny bit denser become noticeably denser. Regions that started slightly emptier become voids, as their matter is pulled away toward the growing concentrations. But the universe isn't static, it's expanding, and that expansion fights against gravity's tendency to pull everything together. In the densest regions, gravity wins, and matter clumps together into what we call halos, roughly spherical concentrations of dark matter. In the less dense regions, gravity can only partially resist expansion, creating filaments and sheets where matter collects but doesn't fully collapse. And in the voids, expansion wins completely, leaving vast, empty bubbles in the cosmic foam. The result, after billions of years of simulated time, looks remarkably like what we observe in the real universe. The digital dark matter forms a web of filaments connecting dense nodes, with vast empty regions in between. It's not exactly like a spider's web. The structure is three-dimensional and far more complex. But the metaphor captures something essential about its nature. It's a connected network, a scaffolding that spans the observable universe. One of the most famous of these simulations is called the Millennium Run, completed in 2005. It followed the evolution of more than 10 billion dark matter particles over 13 billion years of cosmic history, creating a digital universe large enough to contain millions of galaxies. The images it produced are haunting in their beauty, delicate tendrils of matter threading through emptiness, nodes of bright concentration where filaments intersect, and enormous dark voids where almost nothing exists. Looking at these simulations is like seeing the skeleton of the universe laid bare. The cosmic web is the framework upon which everything else hangs, and the truly remarkable thing is that we can verify it's real. We can check the simulation against reality by mapping where galaxies actually are in space, and comparing that distribution to what the dark matter simulations predict. For decades now, astronomers have been conducting galaxy surveys, vast census-taking projects that measure the positions and distances of millions of galaxies, projects with names like the Sloan Digital Sky Survey, the 2DF Galaxy Redshift Survey, and more recently the Dark Energy Survey. Each survey adds millions more galaxies to our maps, filling in the three-dimensional structure of the universe in ever greater detail. And what these surveys reveal is that galaxies indeed follow the pattern predicted by dark matter simulations. They cluster along filaments, gather at nodes, and avoid the voids. When you plot the positions of millions of galaxies in space, the cosmic web emerges from the data like a photograph slowly developing in a dark room. The match between simulation and observation is so precise that it's become one of the strongest pieces of evidence we have that dark matter exists and that our understanding of how it shapes structure is fundamentally correct. But here's where it gets even more interesting. Dark matter doesn't just create the large-scale architecture, the filaments and voids and nodes. It also determines where individual galaxies form and how massive they become. Each galaxy sits inside its own dark matter halo, a roughly spherical cloud of invisible matter that can extend 10 times farther than the visible galaxy itself. Think of it like this. The stars and gas we see are like a bright flame burning at the centre of a vast invisible lantern. These halos form through a hierarchical process. Small halos form first in the early universe, from the first density fluctuations to collapse under their own gravity. Then these small halos merge together, building larger and larger structures over cosmic time. Two small halos collide and merge, creating a more massive halo. That larger halo merges with another and another, gradually building up the massive dark matter cocoons that now surround giant galaxies like our own Milky Way. This hierarchical assembly explains something that long puzzled astronomers: why we see dwarf galaxies orbiting larger galaxies like satellites. Our Milky Way has dozens of these small companions, tiny galaxies with just millions or billions of stars, compared to our hundreds of billions. Computer simulations show that these satellite galaxies likely formed in their own small dark matter halos, which were then captured by the Milky Way's much larger dark matter halo. The satellites are still there, orbiting within our galaxy's dark matter sphere, like moons circling a planet. There's even evidence of this hierarchy within our own cosmic neighbourhood. The local group, the gravitationally bound collection of galaxies that includes the Milky Way, Andromeda, and dozens of smaller galaxies, sits within its own dark matter structure, and the local group itself is part of a larger supercluster called Laniakea, a cosmic structure spanning 500 million light-years. Laniakea, in turn, is just one feature in the larger cosmic web, connected by filaments to other superclusters across the observable universe. It's like those Russian nesting dolls, each one containing a smaller version inside it. Galaxies nest inside dark matter halos. Halos nest inside larger structures. Those structures nest inside superclusters. And superclusters are strung along the filaments of the cosmic web, its structure all the way up, and dark matter is the invisible scaffolding at every level. There's something almost mystical about this when you step back and consider it. Ancient cosmologies often spoke of cosmic architecture, of structure and order imposed on chaos. The Norse had Yggdrasil, the world tree connecting 9 realms. Hindu cosmology described the universe as emerging from the cosmic egg, Hiranyagarbha. Medieval philosophers imagined the great chain of being, an invisible hierarchy connecting everything from the lowest stone to the highest angel. These weren't scientific theories, of course, but they were touching on something real, the human intuition that the universe has structure, that there's an organizing principle beneath the apparent chaos. What's remarkable about the cosmic web is that this invisible architecture actually exists. It's not metaphorical. It's not philosophical abstraction. It's real, measurable, mappable structure that determines where galaxies form and how they evolve over billions of years. And we discovered it through an interesting marriage of observation and computation. The computer simulations told us what pattern to look for. The galaxy surveys confirmed that pattern actually exists. Each one validates the other. The simulations predict, the observations confirm. And in that back-and-forth conversation between theory and reality, we've glimpsed the invisible skeleton of the cosmos. There's also something poetic about how this discovery was made. We couldn't see dark matter directly, so we built digital universes and let simulated dark matter show us what patterns it would create. Then we checked if those patterns existed in the real universe. It's like trying to understand how a puppeteer works when you can only see the puppet. By watching how the puppet moves, you can infer the presence of the strings, the structure of the control frame, even the hand movements of the person pulling the strings, all without seeing any of those things directly. The cosmic web is dark matter's puppet show, and galaxies are the visible puppets dancing on invisible strings. Of course, the simulations aren't perfect. There are still details that don't quite match between the simulated universes and the real one. For instance, the simulations predict more satellite galaxies around large galaxies than we actually observe. They predict denser concentrations of dark matter at the centers of galaxy halos than observations suggest. These discrepancies have names: the missing satellites problem, the cusp core problem, and their areas of active research. Some scientists think these mismatches mean our understanding of dark matter isn't complete, that perhaps dark matter particles interact with each other in ways we haven't accounted for, or that there are additional physical processes affecting how galaxies form within dark matter halos. Others suspect the problem lies in the simulations themselves, that we're not properly modelling all the complicated physics of normal matter. Star formation, supernova explosions, radiation pressure that might alter how gas behaves within dark matter halos. But these are refinements, details to be worked out. The big picture is clear. The cosmic web is real. It's been verified by independent observations, and it's made almost entirely of something we cannot see. In many ways, the cosmic web is the most compelling evidence we have for dark matter's existence. Individual galaxy rotation curves could, in principle, be explained by modifications to gravity. Galaxy cluster masses could potentially be accounted for by exotic forms of normal matter. But the cosmic web, the matching of simulations to observations across billions of light years and billions of years of cosmic time, that's much harder to explain without dark matter. It's the difference between a single clue and a complete pattern. One anomaly might be an error, but when you see the same structure emerging from computer simulations and from real galaxy surveys, when the predicted filaments match the observed filaments, when the simulated voids line up with the empty regions in the actual universe, you're no longer looking at a coincidence. You're looking at the signature of something real, something fundamental about how the universe is built. As you drift towards sleep tonight, you might think about that, about the invisible web that connects one side of the observable universe to the other, about the dark scaffolding that existed before stars, about the hidden architecture that determined where galaxies would form billions of years before Earth coalesced from cosmic dust. Every star you can see, every galaxy in every telescope image, is simply lighting up a structure that was already there, waiting in the dark. Rest in the knowledge that the universe has a shape, a structure, a grand architecture that extends far beyond what our eyes can perceive, and that we've managed to map it through cleverness and patience and the strange partnership between silicon computation and human curiosity. So we know dark matter exists. We can see its gravitational fingerprints in galaxy rotation curves, in cluster dynamics, in the cosmic web itself. But knowing something exists and knowing what it is are two very different things. It's a bit like hearing footsteps in the next room and knowing someone is there, but having no idea whether it's your roommate, a burglar, or the cat knocking things over again. The footsteps are real. The identity of the walker remains mysterious. This is where particle physics enters the story. If dark matter is made of particles, and most scientists believe it is, then what kind of particles could they be? What properties would they need to have? And perhaps most importantly, how might we actually detect them? The search for dark matter particles has led physicists to propose a veritable menagerie of candidates, each stranger than the last. They've been given names that range from the whimsical to the technical, from WIMPs to axions, from sterile neutrinos to primordial black holes. It's a particle zoo, and we're going to take a slow walk through it, pausing to admire each peculiar creature in turn. Let's start with the leading candidate, the one that's received the most attention and the most experimental effort over the past few decades. Meet the WIMP, the weakly interacting massive particle. Now, before you start feeling sorry for this particle based on its unfortunate acronym, let me assure you that WIMPs are actually quite popular in physics circles. The name is descriptive rather than judgmental. These particles, if they exist, would be weakly interacting, meaning they barely interact with normal matter at all. And they'd be massive, at least by particle physics standards, perhaps tens or hundreds of times heavier than a proton. The beauty of WIMPs lies in what physicists call the WIMP miracle, though calling it a miracle might be overselling it slightly. Here's the idea. In the early universe, when everything was extremely hot and dense, particles and antiparticles were constantly being created from pure energy and then annihilating back into energy. As the universe expanded and cooled, these creation and annihilation processes eventually froze out, leaving behind a relic abundance of certain particles. Now, here's the miraculous part. If you calculate how many WIMPs should have survived this freeze-out process, given reasonable assumptions about their mass and how weakly they interact with other particles, you get a number that's remarkably close to the amount of dark matter we observe in the universe today. It's like ordering a pizza and having it arrive exactly when you get hungry, without you having specified a delivery time. The timing just works out. This WIMP miracle isn't proof that dark matter is made of WIMPs. Coincidences do happen after all. But it's suggestive enough that physicists have spent decades building increasingly sensitive detectors to try to catch one of these elusive particles. WIMPs arise naturally from a theoretical framework called supersymmetry, which is itself a beautiful but as yet unproven extension of the standard model of particle physics. Supersymmetry proposes that every particle we know has a heavier supersymmetric partner. The electron has a selectron. The quark has a squark. Yes, these are the actual names physicists use, and yes, they sound like rejected Pokémon. The lightest of these supersymmetric particles, perhaps the neutralino or the gravitino, could be stable, abundant, and massive enough to be dark matter. But WIMPs aren't the only candidates in our particle zoo. Let's wander over to another enclosure and meet the axion. The axion was originally proposed to solve a completely different problem in particle physics called the strong CP problem, which has to do with why the strong nuclear force doesn't seem to violate certain symmetries that it theoretically could violate. I realise that sounds abstract, and honestly, the details aren't crucial for our gentle evening journey. What matters is that physicists Roberto Peccei and Helen Quinn proposed a solution to this problem in 1977, and a consequence of their solution was the prediction of a new particle. This particle was later named the axion by physicist Frank Wilczek after a laundry detergent, because it cleaned up the strong CP problem. You have to admire the sense of humour in theoretical physics. Here you have one of the most profound mysteries in cosmology, and one of the leading candidates for solving it is named after a product for removing grass stains from soccer uniforms. Axions, if they exist, would be extraordinarily light, billions of times lighter than an electron. They'd also interact so weakly with normal matter that trillions of them could be passing through your body right now without you noticing. In fact, some calculations suggest that axions, if they make up dark matter, would be so abundant that there might be a few trillion of them in every cubic centimetre of space. You're not just sitting in a room. You're sitting in an axion sea, an invisible ocean of particles that flow through walls and planets and stars, as if those solid objects were nothing more than empty space. The interesting thing about axions is that they could solve two problems at once, the strong CP problem and dark matter. That's appealing to physicists who generally prefer theories that explain multiple phenomena, rather than theories that require separate explanations for each mystery. It's the cosmic equivalent of a combination tool, a Swiss Army knife of particle physics. Then there are sterile neutrinos. Regular neutrinos, the ones we know exist, are already pretty ghostly. They barely interact with matter. Billions of them from the sun pass through your body every second without leaving any trace. They have a tiny bit of mass, but not nearly enough to account for dark matter. Sterile neutrinos would be even more elusive cousins of these already elusive particles. The term sterile here means they wouldn't interact through the weak nuclear force, which is the primary way regular neutrinos interact with other particles. They'd be completely sterile from the perspective of the forces we usually use to detect particles, interacting only through gravity. They'd be heavier than regular neutrinos, possibly heavy enough to make up dark matter, and they'd be left over from the early universe in sufficient quantities to match observations. Sterile neutrinos have the advantage of being a relatively conservative proposal. They don't require entirely new physics beyond the standard model. They're just an extension of particles we already know exist. They're like finding out your neighbor has a shy sibling who never comes to social gatherings but definitely exists. Now, let's consider something entirely different. What if dark matter isn't made of exotic new particles at all, but of familiar objects that simply don't shine? What if it's made of black holes? Not the massive black holes formed by collapsing stars. Those would be made from normal matter and wouldn't solve our dark matter problem. Instead, we're talking about primordial black holes. Tiny black holes that could have formed in the first fraction of a second after the Big Bang, when the universe was so dense that quantum fluctuations could create black holes directly from the extreme conditions of the early cosmos. These primordial black holes could range in mass from incredibly tiny, smaller than an atom, to dozens of times heavier than the sun. They'd be invisible, as black holes are, and they'd interact gravitationally with everything around them, just as dark matter should. In recent years, there's been renewed interest in this idea, particularly for primordial black holes in a specific mass range that's hard to rule out with current observations. The appeal of primordial black holes is that they wouldn't require any new particle physics. General relativity, which we understand quite well, predicts that black holes can form under the right conditions. If those conditions existed in the early universe, then dark matter might simply be an enormous population of small black holes scattered throughout space, invisible but gravitationally present. There are other candidates too, each with their own quirks and appeal. Some physicists have proposed self-interacting dark matter, particles that barely interact with normal matter, but do interact with each other, perhaps solving some of the discrepancies between simulations and observations in the distribution of dark matter within galaxies. Others have suggested warm dark matter, particles that were moving relatively fast in the early universe, which would affect how structure formed on small scales. There's even a candidate called the WIMP-zilla, basically a WIMP but absurdly massive, perhaps 1 trillion times heavier than a proton. The name alone suggests that physicists were having fun when they proposed it. What all these candidates have in common is that they're consistent with what we observe about dark matter. They'd be stable over billions of years. You don't want your dark matter particles decaying away, or there wouldn't be any left in the universe today. They'd interact gravitationally, because that's how we detect dark matter's presence, and they'd either not interact electromagnetically at all, or interact so weakly that they're effectively invisible to light. But here's the challenge. Multiple candidates can fit the same observations. It's like a crime scene where several suspects all had the opportunity and the means. The rotation curve of a galaxy doesn't tell you whether dark matter is made of WIMPs, axions, or sterile neutrinos. It just tells you that something with mass is there. The cosmic web looks the same whether it's woven from one type of dark matter particle or another. This is why physicists have built such elaborate experiments to try to detect dark matter directly. We need to catch it in the act, to find some way to make it reveal itself beyond its gravitational effects. It's not enough to know the invisible scaffolding is there. We want to know what it's made of, to touch it directly, rather than inferring its presence from the way visible matter behaves. The search for dark matter particles is one of the great detective stories in modern science. We have a suspect. Actually, we have several suspects, a whole lineup of them, but we need evidence. We need to eliminate possibilities, narrow down the candidates, and ideally, find the smoking gun that tells us definitively what dark matter is made of. What makes this search particularly fascinating is that we're looking for something that, by definition, doesn't want to be found. Dark matter particles, whatever they are, interact so weakly with normal matter that they've evaded detection for nearly a century, despite being the dominant form of matter in the universe. They're the ultimate wallflowers, the cosmic introverts, present in enormous quantities but refusing to participate in any of the interactions we normally use to detect particles. There's something almost philosophical about this. The universe is mostly made of something we can't see, made of particles that slip through our detectors like water through a sieve. We can map its effects, calculate its abundance, trace its influence across billions of light years, but we cannot yet capture a single particle and examine it directly. Different types of dark matter would have formed differently in the early universe, and would behave differently in the cosmos today. WIMPs would have been created in the thermal bath of the early universe, and then frozen out as the cosmos cooled. Axions might have condensed from quantum fields in a completely different way. Primordial black holes would have formed from the collapse of overdense regions in the first moments after the Big Bang. Each candidate tells a different story about cosmic history, about the processes that shape the universe in its infancy. Finding out which candidate is correct wouldn't just solve the dark matter mystery. It would also teach us about conditions in the early universe, about physics at energies we could never reach in particle accelerators, about the fundamental nature of reality at the smallest scales. And there's the possibility, unsettling but real, that dark matter isn't made of any single type of particle. Perhaps there are multiple dark sectors, different families of particles that don't interact with light or normal matter. Perhaps dark matter is composite, made of multiple types of particles bound together in dark atoms or dark molecules. The possibilities multiply the more you think about them. For now, all these candidates remain just that, candidates, possibilities waiting to be confirmed or ruled out. The particle zoo remains open for visiting, but we're still trying to figure out which animals actually live there, and which are just theoretical constructs, imagined creatures that seem plausible, but don't actually exist. As you settle deeper into rest, you might find it oddly comforting that the universe still has such profound mysteries, that the majority of all matter takes a form we haven't yet identified, that somewhere in this zoo of exotic particles might be the answer to one of cosmology's deepest questions. The axions or WIMPs or sterile neutrinos or primordial black holes don't care whether we find them. They've been here all along, invisible and patient, waiting in the dark spaces between stars, holding the cosmos together with their gentle gravitational pull, unconcerned with our attempts to give them names or understand their nature. And tomorrow, in laboratories deep underground and in telescopes scanning the sky, scientists will continue their patient search, hoping that one day one of these invisible particles will finally reveal itself. There's something almost monastic about the search for dark matter. Not the searching itself, which involves cutting-edge technology and sophisticated physics, but the location where it happens. To find the most elusive particles in the universe, scientists have gone deep underground into old mines and mountain caverns, creating laboratories in spaces that feel more like medieval crypts than modern research facilities. Why underground? The answer has to do with noise. Not acoustic noise, the laboratories are actually quite silent, but particle noise. Cosmic rays, high-energy particles from space, rain down on Earth's surface constantly, millions of them passing through every square meter every second. These cosmic rays can trigger detectors, creating false signals that would drown out the faint whisper of a dark matter-particle collision. It's like trying to hear a pin drop in a thunderstorm. But cosmic rays are stopped by matter, rock specifically. Go deep enough underground, a mile or more, and the rock above you filters out nearly all the cosmic rays, leaving a much quieter environment. It's cosmic shielding, natural and effective. Down in these depths, detectors can listen for dark matter in relative peace, waiting for the exceedingly rare moment when a dark matter particle might actually interact with normal matter. The largest and most sensitive of these underground laboratories reads like a geography lesson in remote places. There's the Sudan Underground Laboratory in Minnesota, built in an old iron mine half a mile underground. The Gran Sasso National Laboratory in Italy, buried beneath a mountain in the Apennines, accessed through a highway tunnel. The Sanford Underground Research Facility in South Dakota, in what was once the Homestake Gold Mine, now extending more than a mile beneath the Black Hills, and the Kamioka Observatory in Japan, built in an old zinc mine in the Japanese Alps. These aren't small operations. Some of these laboratories occupy caverns large enough to hold cathedrals. The Gran Sasso Lab, for instance, has 3 enormous halls carved into the mountain, connected by tunnels housing dozens of experiments. When you see photographs of these spaces, vast chambers carved from living rock, filled with gleaming detectors and tangles of cables, they do look rather like underground cathedrals. Modern temples dedicated to the pursuit of invisible truths. And like monks in contemplation, the detectors wait. They wait with extraordinary patience, watching for events that might happen only a few times per year, or perhaps not at all. Some experiments have run for decades without detecting dark matter, accumulating null results with the same dedication others might collect positive data. The detectors themselves come in various designs, each based on different principles but all sharing the same basic hope, that a dark matter particle will, on rare occasion, bump into a normal atomic nucleus hard enough to create a signal we can detect. It's a bit like hoping to notice when a ghost brushes past you in a dark room. Most of the time, nothing happens. But if something does happen, you want to be paying very close attention. One common design uses liquid xenon, an element that's normally a gas, but becomes liquid when cooled to about -100 degrees Celsius. The xenon is held in an incredibly pure chamber. Any contamination could create background signals that mimic dark matter. When a particle interacts with a xenon atom, it creates a tiny flash of light and frees some electrons. Both the light and the electrons can be detected, allowing scientists to determine where the interaction happened and how much energy was deposited. These xenon detectors have wonderful names: Elux, Xenon 1T, Panda X. They've grown larger over the years as scientists have realized that to catch something as elusive as dark matter, you need a lot of target material. The latest generation contains tons of liquid xenon, creating volumes large enough that if a dark matter particle does interact, there's a reasonable chance it will hit something. Other experiments use germanium crystals, cooled to just above absolute zero, waiting to feel the tiny vibration, a phonon, in physics terminology, created if a dark matter particle strikes a germanium nucleus. These detectors are so sensitive they can detect temperature changes of a few millionths of a degree. Imagine a thermometer so precise it could tell you whether a snowflake landed on a frozen lake a mile away. That's the level of sensitivity we're talking about. Then there are bubble chamber detectors, which sound charmingly retro and actually work on a principle not unlike those toys from the 1990s, where you'd press a button and bubbles would form in coloured liquid. These detectors use superheated liquids held at a temperature where they should boil but haven't yet. When a particle interaction provides the tiny bit of energy needed, it triggers a bubble to form. Cameras photograph the bubbles and scientists analyse which ones might have been caused by dark matter versus other particle interactions. The challenge with all these detectors is distinguishing dark matter signals from background noise. Even a mile underground, cosmic rays aren't completely absent. Radioactive decay in the rock walls produces particles. Radioactive contamination in the detector materials themselves can create signals. Even the researchers working with the detectors produce background. Humans are slightly radioactive, emitting particles from potassium-40 and carbon-14 in our bodies. So the experiments employ elaborate shielding. The detectors sit inside water tanks that absorb stray particles. They're surrounded by lead bricks, ancient lead sometimes, salvaged from Roman shipwrecks because lead that's been underwater for 2,000 years has had time for its natural radioactivity to decay to negligible levels. Modern lead, freshly smelted, contains traces of radioactive isotopes from nuclear weapons testing and is too hot for the most sensitive experiments. The detectors themselves are built from the purest materials scientists can create. Every component is screened for radioactivity. The xenon is distilled again and again to remove any trace of radioactive krypton. The copper used in construction is selected for extremely low uranium content. Cleanroom protocols would make a hospital operating room look casual by comparison. And still, with all this effort, the detectors see mostly nothing. Or rather, they see a few events per year that might be dark matter, or might be background, and distinguishing between the two is where things get philosophically interesting. One experiment called DAMA/LIBRA in the Gran Sasso Laboratory has reported what they claim is a dark matter signal for over 20 years. The signal has a peculiar characteristic. It varies with the seasons. The idea is that as Earth orbits the Sun, we move through the dark matter halo surrounding our galaxy. For part of the year, Earth's orbital motion is in the same direction as the solar system's motion through the galaxy, so we're moving faster relative to the dark matter. 6 months later, we're moving in the opposite direction, slower relative to the dark matter. This should create a seasonal variation in the rate of dark matter collisions, more in June, fewer in December, or vice versa depending on which direction the solar system is moving. DAMA/LIBRA sees this seasonal variation. They've been seeing it consistently for 2 decades. It's statistically significant, meaning it's unlikely to be a random fluctuation, and yet no other experiment has confirmed it. Multiple other detectors using different techniques but looking for the same dark matter particles see nothing. This has created one of the most enduring puzzles in dark matter physics. Either DAMA/LIBRA has detected dark matter, and we don't understand why other experiments haven't confirmed it, or their signal is from some other seasonal effect they haven't identified. Science is filled with these kind of tensions, these ambiguities that persist for years. Most scientists are skeptical of the DAMA/LIBRA result, given the lack of confirmation from other experiments. But the Italian team continues to stand by their data, and the mystery remains unsolved. It's a reminder that even in our most sophisticated experiments, uncertainty can linger. The null results from other experiments aren't failures, though. Every time a detector runs for months or years without seeing dark matter, it tells us something. It sets limits. If dark matter particles interacted with normal matter above a certain strength, these detectors would have seen them. They haven't, so we can rule out certain types of dark matter. Each null result narrows the parameter space, pushing the remaining possibilities into smaller and smaller corners of the theoretical landscape. It's like a cosmic game of 20 questions, except instead of 20 questions, we've asked thousands, and the universe keeps answering no, while occasionally being ambiguous enough to keep us wondering. Are dark matter particles lighter than we thought? Do they interact even more weakly than our models predicted? Are we looking for the right kind of interaction entirely? Some experiments are now looking for different signatures. Instead of waiting for dark matter to bump into a nucleus, they're looking for dark matter particles to produce light directly, or to interact with electrons rather than atomic nuclei, or even to decay very rarely into particles we can detect. Each approach requires different detector designs and different underground facilities. There's something beautifully stubborn about this enterprise. Imagine dedicating your career to building and running an experiment that might never detect anything. Some researchers have spent 20 or 30 years working on dark matter detection experiments without finding dark matter. Their life's work, measured by traditional metrics, has been a series of increasingly precise ways of not finding what they're looking for. And yet, this is valuable work. These null results have taught us enormous amounts about what dark matter isn't. They've pushed detector technology to extraordinary levels of sensitivity. They've developed techniques for creating ultra-pure materials and ultra-quiet environments that have applications beyond dark matter searches. And they've demonstrated a kind of patience that's rare in modern science, a willingness to pursue a question even when the answer remains elusive decade after decade. The researchers who work in these underground laboratories have chosen a peculiar path. They descend into mines and caverns, into spaces where sunlight never reaches, where the only illumination comes from artificial lights and the occasional glow of a computer screen. They work with detectors that spend most of their time seeing nothing, waiting for signals that may never come. In some sense, they've become modern anchorites, dedicated to a search for the invisible, willing to spend years in the depths for the possibility of a single moment of revelation. There's a certain romance to it. The old mines where these laboratories are built were once places where people descended seeking gold, iron, zinc, tangible treasures pulled from the earth. Now, they're places where scientists descend seeking something far more elusive, knowledge about the fundamental nature of the universe, answers to questions about what most of reality is made of. The underground setting adds to this sense of seeking hidden truth. Throughout human history, we've associated deep places with mystery and revelation. The oracle at Delphi delivered prophecies from a chasm in the earth. Medieval mystics sought enlightenment in caves and grottos. The Greek underworld, Hades, was where hidden truths about death and fate resided. There's something archetypal about descending into darkness to seek what cannot be found in the light of day. Of course, the scientists working in these facilities would probably roll their eyes at such poetic interpretations. They're there because the physics demands it, because cosmic ray shielding requires rock overhead, because sensitive detectors need quiet environments. The mysticism is accidental, a byproduct of practical requirements. But still, there's something that resonates. These underground chambers with their massive detectors waiting in silence, their researchers checking data year after year, their dedication to finding something that has eluded. As you sink deeper into rest, you might think about those detectors, still running tonight as you sleep. Deep underground in South Dakota, in Italy, in Japan, in China, they're watching, waiting for dark matter particles to drift through the earth, through the rock, through the shielding, through the detector materials, and just once, just rarely, to interact with a xenon atom or a germanium nucleus strongly enough to leave a trace. The detectors will keep watching through the night, through tomorrow, through next year, as patient as the rock that surrounds them, as dedicated as the researchers who built them, waiting in the dark for the invisible to finally reveal itself. Light travels in straight lines. This is one of those facts that seems so obvious, so fundamental, that questioning it feels almost absurd. Look across a room and light travels directly from the lamp to your eye. Shine a laser pointer, and the beam cuts a perfectly straight path through the air. It's geometry, simple and clean. Except it's not quite true. Light doesn't always travel in straight lines. When it passes near something massive, a star, a galaxy, a cluster of galaxies, the fabric of space itself curves, and light follows that curve. It's not that the light is bending exactly, it's that space is bent, and light is simply taking the shortest path through curved space, which from our perspective looks like a bent path. This is gravitational lensing, and it's become one of our most powerful tools for mapping dark matter. Because while dark matter doesn't interact with light directly, doesn't emit it, doesn't absorb it, it does have mass and mass-curved space. So dark matter acts as an invisible lens, bending the light from distant galaxies as it passes through the dark matter halos and filaments between us and them. The effect was predicted by Einstein's general relativity in 1915, but it took decades before astronomers had telescopes powerful enough to observe it clearly. Now, we see it everywhere we look in the deep universe. Distant galaxies appear distorted, stretched into arcs and rings by the gravitational lensing of massive objects in the foreground. Sometimes a single background galaxy is imaged multiple times, its light taking different paths around a foreground cluster and arriving at our telescopes from slightly different directions. These lensed images are beautiful in their own right. Einstein rings, perfect circles of light, formed when a distant galaxy, a massive foreground object, and Earth are almost perfectly aligned, look like cosmic jewelry, delicate halos of light suspended in the darkness. Gravitational arcs curve gracefully around galaxy clusters, stretched and magnified by the invisible mass bending space around them. But they're more than just beautiful. They're tools. By measuring how much a background galaxy's light is bent, astronomers can calculate how much mass must be present in the foreground to cause that bending. It's like being able to weigh something by watching how it deflects light, measuring the invisible by its effects on the visible. And what these measurements reveal, again and again, is that there's far more mass present than we can see. Galaxy clusters that appear to contain a few hundred galaxies are bending light as if they contain thousands. The lensing signal shows the presence of vast dark matter halos, invisible cocoons surrounding the visible galaxies, stretching far beyond where the stars and gas clouds end. There are two main types of gravitational lensing that astronomers use to study dark matter. Strong lensing is the dramatic kind, the Einstein rings and multiple images, the cases where the lensing effect is so pronounced you can see it clearly in images. These occur when light passes very close to a massive foreground object, usually a galaxy cluster, and the bending is severe enough to create obviously distorted or multiplied images. Strong lensing events are rare, requiring nearly perfect alignment between the background source, the lens, and the observer. But when they happen, they provide incredibly detailed information about the mass distribution of the lensing object. Astronomers can create models of how mass is distributed in a galaxy cluster and refine those models until the predicted lensing pattern matches what's actually observed. The match has to be precise. The positions, shapes, and brightnesses of multiple lensed images all constrain the mass distribution. What's remarkable is that these models consistently show that most of the mass in galaxy clusters is not where the galaxies are. The galaxies trace out the locations of visible matter, but the gravitational lensing reveals that the bulk of the mass is distributed more smoothly in a roughly spherical halo that extends far beyond the visible cluster. Dark matter, making its presence known through the geometry of bent light. Then there's weak lensing, which is more subtle but in some ways more powerful. Weak lensing doesn't create dramatic rings or multiple images. Instead, it causes slight distortions in the shapes of background galaxies. They become slightly more elliptical, stretched in particular directions. Any individual galaxy's distortion is too small to measure reliably. It could just be that the galaxy happens to be elliptical naturally. But when you look at thousands of background galaxies all behind the same foreground structure, a pattern emerges. If dark matter is present in the foreground, it will cause the background galaxies to be preferentially stretched in a coherent way, all distorted in directions that point back to the dark matter concentration. It's like looking at grass bent by wind. Any single blade might be bent for various reasons, but if you see thousands of blades all bent in the same direction, you know something systematic is affecting them. Weak lensing surveys have mapped dark matter across enormous volumes of the universe. Projects like the Dark Energy Survey, the Kilo Degree Survey, and the upcoming Legacy Survey of Space and Time will measure the shapes of billions of galaxies, creating three-dimensional maps of dark matter distribution that reveal the cosmic web in unprecedented detail. These maps show filaments connecting galaxy clusters, sheets of dark matter extending across hundreds of millions of light years, and voids where very little mass exists. They confirm what the computer simulations predicted, that dark matter forms a scaffolding, a web-like structure that visible matter follows. The galaxies are like Christmas lights strung along the framework, illuminating a structure that extends far beyond what shines. Perhaps the most compelling evidence for dark matter from gravitational lensing comes from colliding galaxy clusters. When two galaxy clusters merge, it's one of the most energetic events in the universe, releasing as much energy as billions of supernovae, and it provides a unique opportunity to see dark matter and normal matter behaving differently. The most famous example is the Bullet Cluster, discovered in observations taken in the early 2000s. It's actually two galaxy clusters that have passed through each other at speeds of millions of miles per hour. When the collision happened, the normal matter, the hot gas that fills the space between galaxies in a cluster, interacted. The gas clouds from the two clusters collided, heated up and slowed down, creating a shock wave visible in X-ray observations. But the dark matter, which makes up most of each cluster's mass, doesn't interact that way. Dark matter particles pass through each other almost without noticing, like two swarms of bees interpenetrating. So while the gas clouds crashed together and slowed down, the dark matter halos just kept going, passing through each other and emerging on opposite sides of the collision. Gravitational lensing reveals this clearly. The X-ray observations show where the normal matter is, the glowing hot gas at the collision site. But the gravitational lensing signal, which shows where the mass is, doesn't match the X-ray emission. The mass is displaced from the gas, offset in exactly the way you'd expect if most of the mass was dark matter that passed through the collision while the gas stopped. It's like watching two moving trucks crash into each other. The trucks stop at the collision point, but their cargo, if it wasn't well secured, might keep moving forward, sliding off the truck beds and ending up past the crash site. In the bullet cluster, the gas is the trucks, stopped by the collision. The dark matter is the cargo, continuing forward because it didn't interact during the collision. This observation is difficult to explain without dark matter. If you wanted to modify gravity instead of invoking dark matter, you'd expect the gravitational anomaly to be centered on the visible matter, on the gas clouds at the collision site. But it's not. The lensing signal is offset from the visible matter in precisely the pattern you predict if most of the mass was in invisible dark matter halos that pass through the collision. Several other colliding clusters have been found since the bullet cluster, and they show similar separations between the visible matter and the gravitational lensing signal. Each one is another piece of evidence that dark matter exists as actual particles that can be separated spatially from normal matter under the right circumstances. The cosmic microwave background radiation, the ancient light from when the universe first became transparent, just 380,000 years after the Big Bang, also carries fingerprints of dark matter. The tiny temperature variations in this radiation, differences of just a few millionths of a degree across the sky, encode information about the density of matter in the early universe. And the pattern of these variations, their size scale, their amplitude, how they correlate across different distances, depends crucially on how much dark matter was present. The measurements are extraordinarily precise. Satellites like WMAP and Planck have mapped the cosmic microwave background in exquisite detail, and the data matches theoretical predictions for a universe containing about 27% dark matter and 5% normal matter, with the rest being dark energy. Change the amount of dark matter, and the predicted pattern of temperature fluctuations changes in ways that no longer match observations. There's also a phenomenon called baryon acoustic oscillations, which sounds technical, but has a certain poetry to it. In the early universe, before the cosmic microwave background was emitted, pressure waves, sound waves essentially, travelled through the hot plasma, creating ripples in the density of matter. When the universe cooled enough for atoms to form, these sound waves froze in place, leaving a characteristic scale imprinted in the distribution of matter. Today we can see this characteristic scale as a slight excess in the number of galaxy pairs, separated by about 500 million light-years. It's like finding a preferred distance between objects, a cosmic ruler left over from the early universe. The length of this ruler depends on the conditions in the early universe, including the amounts of normal matter and dark matter, and once again observations match predictions for the amounts of dark matter we infer from other methods. All these different techniques, gravitational lensing, the cosmic microwave background, baryon acoustic oscillations, galaxy cluster masses measured through X-ray emissions and the motion of galaxies, they all point to the same conclusion. They give consistent values for how much dark matter exists and how it's distributed. This concordance of independent measurements is powerful evidence. It's one thing for a single observation to suggest dark matter. It's quite another for multiple completely different techniques, based on different physics and different observations, to all converge on the same answer. It's like a crime investigation where witnesses saw different parts of the crime from different angles. Physical evidence was collected from multiple locations, and security cameras captured the event from various viewpoints. Each piece of evidence alone might be questionable, but when they all tell the same story, the case becomes compelling. Dark matter's fingerprints are everywhere, in bent light, in the cosmic microwave background, in colliding clusters, in the large-scale structure of the universe, and they all point to the same invisible presence. Future telescopes will push these techniques even further. The Nancy Grace Roman Space Telescope, launching later this decade, will conduct massive weak lensing surveys, measuring the shapes of billions of galaxies, and creating three-dimensional dark matter maps with unprecedented resolution. The Vera Rubin Observatory, named after the astronomer whose galaxy rotation curves helped establish dark matter's existence, will survey the entire visible sky every few nights, tracking how gravitational lensing changes over time as matter moves and evolves. These observations won't tell us what dark matter is made of. That requires direct detection or production in particle accelerators. But they'll refine our understanding of how dark matter behaves, how it clusters, how it shaped the formation of galaxies, and the evolution of cosmic structure. They'll test whether dark matter is purely cold and collisionless, or whether it might have subtle interactions we haven't detected yet. As you drift toward deeper rest, consider that light itself has become our telescope into the invisible. The bending of light by dark matter's gravity lets us map what we cannot see directly, trace the outline of the cosmic scaffolding, weigh the universe and find it full of invisible mass. Every photon that travels across billions of light years carries information not just about its source, but about everything it passed near during its journey. Every dark matter filament that slightly deflected its path, every halo that gently curved its trajectory. In the subtle distortions of distant galaxies, in the patterns of ancient light, dark matter writes its signature across the cosmos, invisible but not undetectable, present in the geometry of space itself. There's a principle in philosophy and science called Occam's razor, which suggests that when multiple explanations fit the observations, the simplest one is usually correct. It's a useful guideline, though simple can be surprisingly hard to define. Is it simpler to propose that 85% of the universe is made of invisible particles we've never detected? Or is it simpler to suggest that our understanding of gravity, tested and verified countless times in our solar system, might need adjustment when applied to larger scales? This is the central question behind alternative theories to dark matter. Maybe, these theories suggest, there isn't any invisible matter at all. Maybe galaxies rotate the way they do not, because they're embedded in dark matter halos, but because gravity itself behaves differently than we think it does on galactic scales and larger. Maybe the problem isn't missing matter, but incomplete physics. The most prominent of these alternatives is called MOND, Modified Newtonian Dynamics. It was proposed in 1983 by an Israeli physicist named Mordechai Milgram, who had been pondering the same galaxy rotation curves that convinced most astronomers dark matter existed. But Milgram looked at those flat rotation curves and saw a pattern that suggested something different. Here's what caught his attention. There seemed to be a characteristic acceleration where the strangeness began. In the inner parts of galaxies, where stars orbit relatively quickly and experience strong gravitational acceleration, Newtonian physics worked fine. But in the outer regions, where accelerations are very small about 1/10 billionth of the acceleration you experience standing on Earth's surface, the rotation curves stopped following Newton's predictions and became flat. Milgram proposed a modification to Newton's laws. At high accelerations, gravity behaves exactly as Newton described, but below a certain threshold, that characteristic acceleration where the flatness begins, gravity becomes stronger than Newton predicted. The strengthening is just enough to explain the flat rotation curves without invoking dark matter. The elegance of MOND is that it works. For spiral galaxies, it predicts rotation curves that match observations remarkably well, often better than dark matter models that haven't been carefully tuned. Feed MOND the distribution of visible matter in a galaxy, and it will tell you how that galaxy should rotate. Compare that prediction to actual observations, and you'll find a surprisingly good match. This is no small achievement. MOND, with a single new principle, that gravity behaves differently at low accelerations, can explain something that otherwise requires invoking 5 times as much invisible matter as visible matter. From a certain perspective, modifying one law seems more economical than inventing an entirely new substance that makes up most of the universe. But there are problems. MOND works well for individual spiral galaxies, but it struggles with galaxy clusters. The motions of galaxies within clusters, the temperatures of the hot gas, the gravitational lensing signals, all of these suggest more mass than visible matter, even when you apply MOND's modified gravity. Milgram and other MOND proponents have suggested that perhaps there's some matter missing in clusters, just not as much as conventional dark matter theories require. But this starts to feel like a compromise, like modifying gravity and still needing some dark matter. More seriously, MOND has trouble with the cosmic microwave background and the large-scale structure of the universe. The patterns in the ancient light, the growth of cosmic structure over time, the baryon acoustic oscillations, these observations seem to require dark matter in the early universe before galaxies even formed. MOND was designed to explain galaxy rotation curves, and it does that well, but extrapolating it to cosmological scales has proven difficult. Over the years, theorists have developed relativistic versions of MOND, theories that modify Einstein's general relativity rather than just Newton's simpler laws. The most well-known is TVS, Tensor Vector Scalar Gravity, proposed by physicist Jacob Bekenstein. TV's attempts to extend MOND into a full theory of gravity that could replace general relativity in all contexts, not just galaxy rotation curves. But these relativistic theories bring their own complications. They often require additional fields permeating space, new forces that couple to matter in specific ways, and adjustable parameters that need to be tuned to match observations. By the time you've built a relativistic MOND theory that works for both galaxies and cosmology, you've created something quite complex, arguably more complex than simply accepting that dark matter exists. There are other alternative theories, each approaching the problem from different angles. Some propose that gravity emerges from deeper quantum mechanical principles, that space-time itself is not fundamental, but arises from more basic entities. Erik Verlinde, a Dutch theoretical physicist, suggested that gravity might be an entropic force, similar to how pressure emerges from the random motion of molecules, even though individual molecules don't exert pressure. In this view, dark matter effects would arise from how information is distributed in space, rather than from actual dark matter particles. These emergent gravity theories are intellectually fascinating, touching on deep questions about the nature of space-time and quantum mechanics. But they're also highly speculative, and most haven't been developed to the point where they make testable predictions about galaxy rotation curves or cosmic structure formation. Then there are theories involving extra dimensions. In our everyday experience, space has 3 dimensions: length, width, and height. But some theories in particle physics suggest there might be additional spatial dimensions, curled up so small we don't notice them. Could effects we attribute to dark matter actually be gravity leaking into or out of these extra dimensions? The mathematics of extra dimensions is elegant and has connections to string theory, one of the leading candidates for a unified theory of physics. But again, turning these ideas into concrete predictions for galaxy rotation curves and cosmic structure has proven challenging. Extra dimensions might exist, but whether they can explain dark matter observations remains an open question. What's interesting about all these alternative theories is that they represent different philosophical approaches to anomalous observations. When data doesn't match predictions, you can either modify your inventory of what exists, add dark matter, or modify your understanding of how things behave, modify gravity. Both approaches have historical precedent. In the 19th century, astronomers noticed that Uranus's orbit didn't quite follow Newton's predictions. They had 2 choices: assume Newton's gravity was wrong when applied to the outer solar system, or assume there was another planet out there whose gravity was affecting Uranus. They chose the second option, calculated where that planet should be, and found Neptune almost exactly where predicted. Score 1 for adding new objects rather than modifying physics. But also in the 19th century, astronomers noticed that Mercury's orbit didn't quite follow Newton's predictions. Some suggested there might be another planet, Vulcan, orbiting even closer to the Sun. They looked for decades, but never found it. The real explanation came in 1915 when Einstein's general relativity replaced Newton's gravity with a more accurate theory. Mercury's orbit matched the new predictions perfectly, without requiring any additional planets. Score 1 for modifying physics rather than adding new objects. So which approach is correct for dark matter? Should we believe in invisible particles like Neptune, or should we modify gravity like we did for Mercury? The honest answer is that we don't know for certain, and the decision partly depends on which evidence you find most compelling. The case for dark matter rests on the convergence of multiple independent lines of evidence: galaxy rotation curves, gravitational lensing, the cosmic microwave background, baryon acoustic oscillations, the distribution of galaxies across cosmic time. All of these seem to require dark matter, and they all point to roughly the same amount of it. The consistency across different observations and different techniques is powerful. The case for modified gravity rests on the appeal of not inventing new substances, on the success of MOND for spiral galaxies, and on the philosophical argument that we should be cautious about claiming that most of the universe is made of something we've never detected. There's also the reality that we don't know what dark matter is. We've named it, we've quantified it, we've mapped it, but we haven't captured a single particle or definitively identified what it's made of. Most cosmologists favour dark matter, but not unanimously. MOND continues to have thoughtful proponents who point out weaknesses in dark matter models and successes in galaxy-scale predictions. Scientific conferences on the topic can get surprisingly spirited, with MOND advocates and dark matter proponents debating interpretations of observations and the philosophy of theory choice. There's something refreshing about this uncertainty, this ongoing debate. Science is often presented as a collection of established facts, but active science, science at the frontier, is messier and more interesting. It's a conversation, sometimes a heated one, where smart people examine the same evidence and reach different conclusions based on which principles they prioritize and which observations they find most decisive. It's also worth noting that dark matter and modified gravity aren't necessarily mutually exclusive. Perhaps gravity does behave differently at low accelerations, and there's also some dark matter, just less than conventional models suggest. Perhaps the truth is some hybrid that we haven't thought of yet. Nature has surprised us before with solutions more subtle than the either-or choices we initially considered. The bullet cluster, that colliding galaxy cluster where dark matter and normal matter separated spatially, is often cited as particularly strong evidence against modified gravity. In MOND, gravity is generated by matter. So wherever the matter is, the gravitational anomaly should be centered there too. But in the bullet cluster, the gravitational lensing signal is offset from the visible matter, suggesting the gravitational source isn't where the matter is. This is easy to explain with dark matter. The dark matter halos passed through the collision while the gas stopped, but much harder to explain with modified gravity alone. MOND advocates have proposed explanations, including the possibility that there's some matter in the clusters we're not seeing, or that the collision dynamics in modified gravity are more complex than initially thought. But many physicists see the bullet cluster as tipping the scales decidedly toward dark matter. Still, the debate continues, and that's healthy. Science progresses not just through observations, but through the critical examination of those observations, through challenges to prevailing theories, through the willingness to consider that maybe the majority view is wrong. Most revolutionary scientific discoveries began with a minority view that eventually accumulated enough evidence to shift the consensus. Whether dark matter or modified gravity ultimately proves correct, or whether the answer is something we haven't imagined yet, the process of figuring it out teaches us how to think about the universe, how to weigh evidence, how to remain humble in the face of mystery while still making progress toward understanding. As you settle deeper into rest, you might find it oddly comforting that scientists disagree about something this fundamental, that there isn't unanimous consensus, that the question remains open, that smart people can look at the same observations and reach different conclusions. It means we're still exploring, still questioning, still willing to consider that our maps of reality might need revision. The universe doesn't care whether we call the invisible substance dark matter or an artifact of modified gravity. It simply is what it is, patient and unconcerned with our attempts to name and understand it, waiting for us to gather enough evidence to finally settle the question one way or another. Imagine searching for something for nearly a century and never quite finding it. You'd think at some point you might give up, declare the search futile, move on to easier questions. But scientists are a peculiarly stubborn breed, and the search for dark matter continues with something that looks less like frustration and more like patient determination. Each year brings new experiments, new techniques, new places to look. The search is evolving, becoming more creative, casting wider nets into the cosmic ocean. Those underground detectors we visited earlier, waiting in their cathedral-like chambers deep beneath mountains and old mines, they're getting company. Bigger siblings, more sensitive cousins, experiments that make the current generation look almost quaint by comparison. Darwin, the dark matter, WIMP search with liquid xenon, which sounds like it should be a character in a science fiction novel, will use 40 tons of liquid xenon. 40 tons. That's roughly the weight of several large trucks, all of it ultra-pure liquid, held at -100 degrees, waiting for a single dark matter particle to bump into a single xenon atom. At that scale, if WIMPs exist and interact with normal matter at anything stronger than the faintest whisper, Darwin should see them. It's like replacing your fishing net with one the size of a football field. Something should get caught eventually, assuming there are fish in the ocean you're trawling. There's also Argo, which will use liquid argon instead of xenon, just in case dark matter particles have preferences about what they interact with. It's a bit like offering a variety of snacks at a party, Maybe the guest you're trying to attract doesn't like chips but will take some pretzels instead. These future detectors will run for years, decades perhaps, accumulating data with the patience of monks illuminating manuscripts. They're designed to identify single electron recoils, to measure energy depositions so tiny they're equivalent to feeling a grain of sand fall a millimeter. The sensitivity gains are almost absurd when you think about them. We've built machines that can detect events millions of times fainter than anything we could measure just a few decades ago. But here's where it gets interesting. These detectors are becoming so sensitive that they're starting to run into a problem that's almost poetic. They're becoming sensitive enough to see neutrinos, regular neutrinos, not dark matter at all, just those ghostly particles that stream through everything constantly. Very rarely a neutrino will bump into a nucleus in the detector, creating a signal that looks suspiciously like what a dark matter particle might create. This is called the neutrino flaw, and it represents a kind of fundamental barrier. Below a certain interaction strength, neutrino collisions will create so much background noise that dark matter signals would be drowned out completely. It's like trying to have a whispered conversation at a concert. At some point, the background music is just too loud. Reaching the neutrino flaw would be an achievement in itself, though. It would mean we've built detectors sensitive enough to see individual neutrinos bumping into things, which is remarkable, and it would tell us something definitive. If dark matter particles interact more weakly than this threshold, we need completely different detection strategies. Sometimes learning where not to look is as valuable as finding what you're looking for. Meanwhile, the axion hunters are getting more clever. Axions, those particles named after laundry detergent, would interact with magnetic fields in ways that WIMPs wouldn't. Strong magnets can coax axions into converting into photons, particles of light, which we can then detect. The ADMX experiment in Washington State does exactly this, creating conditions where axions, if they're passing through, might reveal themselves as faint radio signals. The tricky part with axions is that nobody knows exactly what mass they should have. The theory allows for a huge range of possibilities, and the experiments have to scan through this range, like tuning an old analog radio, frequency by frequency, listening for the station that might be broadcasting dark matter. It's slow work, patient work, the kind of work that might take decades to complete. Future action experiments will use arrays of detectors, quantum sensors so sensitive they border on the absurd, and signal processing techniques borrowed from communications technology. They'll search for lighter axions and heavier axions, faster scans and wider frequency ranges. Some will look for axions coming from the sun rather than from dark matter, testing whether these particles exist at all before worrying about whether they make up the invisible scaffolding of the universe. Then there's the indirect approach, which has a certain detective story quality to it. Instead of waiting for dark matter particles to interact directly with our detectors, we can look for the product of dark matter particles interacting with each other. If dark matter particles occasionally annihilate when they meet, matter and antimatter destroying each other in a flash of energy, they should produce gamma rays, neutrinos, or cosmic rays that we might detect from Earth. Space telescopes and ground-based observatories scan the sky looking for these signals, paying particular attention to places where dark matter should be densely concentrated. The centers of galaxies, for instance, or dwarf galaxies that are mostly dark matter with just a few stars lighting them up. If dark matter is destroying itself there, we might see the glow. The challenge is distinguishing dark matter signals from all the other things that produce gamma rays. The center of our galaxy is a messy place, cosmically speaking. There are pulsars spinning and beaming radiation like cosmic lighthouses, supernova remnants glowing with the debris of exploded stars, black holes consuming matter and radiating energy. Claiming that a particular gamma-ray excess comes from dark matter, annihilation, rather than one of these mundane sources requires extraordinary evidence and extremely careful analysis. A few years back, there was genuine excitement about a gamma-ray excess from the galactic center that had some characteristics matching what dark matter annihilation might produce. But further analysis suggested it might actually come from a population of millisecond pulsars, rapidly spinning neutron stars that we can't see individually, but whose collective emission creates the signal. The dark matter interpretation hasn't been ruled out completely, but it's become less compelling as alternative explanations have been explored. This is typical of indirect detection. You see something interesting, something unexpected, and immediately the question becomes, is it dark matter, or is it just the universe being complicated in ways we didn't fully anticipate? Usually it turns out to be the latter. The universe is very good at being complicated. Particle accelerators are joining the hunt too. The Large Hadron Collider at CERN, that enormous ring beneath the Swiss-French border, where protons are smashed together at nearly the speed of light, might be able to create dark matter particles if they're not too heavy. The idea is simple in principle. Collide protons with enough energy and you might create dark matter particles that immediately escape the detector, carrying energy and momentum with them. You wouldn't see the dark matter directly, but you'd notice the missing energy, the imbalance in the collision products. So far, the LHC hasn't seen convincing evidence of dark matter production, but it's still running, still collecting data, and future upgrades will increase its collision energy and improve its detector's sensitivity. If dark matter particles can be created in high-energy collisions, the LHC or its eventual successor might eventually make them. There are more exotic approaches too. Some experiments are using atomic interferometry, essentially using atoms as incredibly sensitive measuring devices that can detect tiny forces or interactions. Others are exploring quantum dots, magnetic monopoles, and techniques that sound more like science fiction than established physics. The diversity of approaches is encouraging. If one method doesn't work, dozens of others are being tried simultaneously. Machine learning and artificial intelligence are also entering the picture, helping to sift through enormous data sets, looking for subtle patterns that might indicate dark matter signals hidden in noise. These algorithms can be trained to recognize the signatures of different types of particle interactions, to distinguish signal from background, with sometimes superhuman precision. Multi-messenger astronomy, combining observations from different types of telescopes and detectors, looking for correlated signals in gravitational waves, neutrinos, gamma rays, and cosmic rays, might provide new ways to detect dark matter or constrain its properties. The idea is that dark matter, if it's doing anything interesting anywhere in the universe, might leave traces in multiple channels simultaneously. But there's also the possibility, uncomfortable but real, that we might never directly detect dark matter particles, not because they don't exist, but because they interact so weakly with normal matter that no conceivable detector would ever catch them. They could be passing through our most sensitive instruments by the trillions every second, and we'd simply never know. This would be frustrating, yes, but it wouldn't mean the search was wasted. We'd have learned an enormous amount about detector technology, about the limits of measurement, about the universe's particle content. We'd know with certainty that dark matter, if it's made of particles, is extraordinarily elusive. And we'd continue mapping it through its gravitational effects, through lensing and cosmic structure, even if we could never hold a dark matter particle in our metaphorical hands. There's also the chance that dark matter isn't a single type of particle, but a whole sector of particles, a dark sector with its own physics, its own forces, perhaps even its own periodic table of elements. In that case, the dark matter we're trying to detect might be composite, made of dark atoms or dark molecules, and our current detection strategies might be looking for the wrong kind of interaction entirely. The search for dark matter has become one of the great sustained efforts in modern physics. Generations of scientists have devoted entire careers to it. Some have spent decades building and running experiments without finding what they sought. But each negative result narrows the possibilities. Each new technique opens new avenues, and the collective effort moves forward, patient and persistent. Tonight, as your thoughts slow and soften, consider the quiet determination of those who search for what cannot be seen. In a world that often demands quick answers and immediate results, the dark matter hunt unfolds across decades and generations. Scientists descending into mines, cooling xenon to unimaginable purities, scanning the sky for faint gamma-ray signals, building detectors of ever-increasing sensitivity, refusing to give up on the question even after nearly a century of searching. Dark matter, if it's out there, is in no hurry to reveal itself. It's been invisible for billions of years and seems content to remain so. But the search continues in underground laboratories and mountaintop observatories, in particle accelerators and space telescopes, in computer simulations and theoretical calculations. Somewhere in this vast effort, in this patient accumulation of technique and data and understanding, might lie the key to finally seeing what has remained hidden for so long. So here we are, at the end of our gentle journey through the invisible cosmos, and you might find yourself in a curious position. You now know that most of the universe is made of something we cannot see, cannot touch, cannot directly detect despite nearly a century of trying. You know that the stars and galaxies we photograph, the nebulae we admire, all the light and colour and visible beauty of the cosmos amounts to less than 15% of what actually exists. This could feel unsettling. It could make the universe seem alien, unknowable, fundamentally mysterious in ways that push against our desire for understanding. But there's another way to think about it, a perspective that might feel oddly comforting as you settle into rest. We are living in a universe that still has profound mysteries, in an age where it sometimes feels like everything has been discovered, mapped, explained, and catalogued. Dark matter reminds us that we've barely scratched the surface, the invisible scaffolding holding galaxies together, shaping the cosmic web, guiding the formation of every star and planet. It's still largely unknown to us. We've named it, mapped its distribution, calculated its abundance, but we haven't touched it. We don't know what it is. That's remarkable when you pause to consider it. We live in the time after the moon landings, after the mapping of the human genome, after the detection of gravitational waves and the imaging of black holes. We've split atoms and sequenced DNA and sent spacecraft to the edge of the solar system. We have remarkable knowledge about how the universe works, from the quantum scale to the cosmic. And yet, 85% of all matter is a complete mystery to us. There's a humility in that realization. For all our technology, all our sophisticated detectors and powerful telescopes, all our theoretical frameworks and mathematical models, we're still fundamentally limited in what we can perceive. We see the universe through a narrow window, the slice of reality that interacts with light and the other forces we can detect. Everything else is invisible to us, present only as a gravitational whisper, a bend in space-time, a mathematical necessity in our equations. Fritz Zwicky saw it first in 1933, watching galaxies move too quickly in their clusters. Vera Rubin confirmed it in the 1970s, measuring the flat rotation curves of spiral galaxies. Since then, generation after generation of astronomers and physicists have added to our understanding, mapping the cosmic web, detecting gravitational lensing, measuring the cosmic microwave background, building ever more sensitive detectors in underground laboratories. Each generation has added pieces to the puzzle. We know more about dark matter than Zwicky could have imagined. We've mapped its distribution across billions of light years. We've traced its influence through cosmic history, from the first moments after the Big Bang to the present day. We've narrowed down what it could be, ruled out countless possibilities, developed sophisticated theories about its nature. But we still haven't found it. Not directly, not conclusively. The particle or particles that make up dark matter remain elusive, slipping through our finest detectors, refusing to reveal themselves despite our increasingly clever attempts to catch them. This long search without definitive success could be seen as a failure. Nearly a century of effort, billions of dollars in funding, thousands of brilliant minds dedicated to the problem, and we still don't know for certain what dark matter is made of. By some measures, that's an extraordinary waste of time and resources. But that's the wrong way to think about it. Science isn't just about finding answers, it's about asking better questions, developing new techniques, expanding our understanding of what's possible. The search for dark matter has pushed technology to extraordinary limits. It's created detectors so sensitive they can feel single atoms recoiling from particle collisions. It's mapped the universe in ways that would have seemed impossible just decades ago. It's brought together particle physicists, astronomers, cosmologists, and engineers in a collaborative effort that spans continents and generations. And it's taught us humility. It's shown us that the universe doesn't care about our timelines, our funding cycles, our desire for quick answers. Dark matter will reveal itself when and if we develop the right techniques to detect it, and not a moment sooner. Until then, it continues its patient existence, holding galaxies together, shaping cosmic structure, completely indifferent to our attempt to understand it. There's something almost zen about that. Dark matter asks nothing of us. It doesn't demand to be understood. It simply is, doing what it's always done, providing the gravitational scaffolding for everything we can see. The stars shine, the galaxies spin, the cosmic web stretches across the universe, all held together by invisible hands that have never needed acknowledgement or recognition. Living in a dark matter universe means accepting that most of reality is hidden from direct perception. It means acknowledging that our senses, powerful as they are, show us only a fraction of what exists. It means being comfortable with uncertainty, with questions that might not have answers in our lifetimes, with mysteries that could persist for generations. But it also means living in a universe that's larger and stranger than it appears. When you look up at the night sky, you're seeing not just the stars, but the faint visible traces of an invisible architecture. Each galaxy sits in its dark matter halo, a cocoon of unseen mass extending far beyond the stars. The space between galaxies isn't empty, but threaded with dark matter filaments, connecting one cluster to another in a vast web that shapes cosmic structure. You're part of that structure. The Milky Way, our home galaxy, sits in a dark matter halo that extends perhaps 10 times farther than the visible disk of stars. As Earth orbits the Sun, and the Sun orbits the galactic center, we're all moving through this dark matter halo, immersed in it, though we can't feel its presence except through gravity's pull. Some estimates suggest that at any given moment, billions of dark matter particles are passing through your body. If dark matter is made of WIMPs, they're streaming through you right now, through the walls of your room, through the entire Earth, barely interacting with the atoms that make up your flesh and bones. You're essentially transparent to dark matter, and it's transparent to you, two forms of matter occupying the same space but barely acknowledging each other's existence. There's poetry in that, in being immersed in something you cannot perceive. It's a reminder that reality extends beyond what our senses tell us, that the universe is larger and more complex than the slice of it we can directly observe. Some people find this unsettling. They want the universe to be fully knowable, completely mappable, eventually understandable in its entirety. The existence of dark matter, of something so fundamental yet so elusive, challenges that desire. It suggests that there might always be aspects of reality that remain mysterious, hidden, just beyond our ability to fully grasp. But others find it comforting. In a cosmos where dark matter exists, there's always something more to discover, always deeper mysteries waiting to be explored. We'll never reach the end of knowledge, never map everything there is to know, never run out of questions to ask. The universe will always have secrets, and that means the adventure of discovery will never truly end. The next few decades will likely bring new developments in the dark matter search. New detectors will reach unprecedented sensitivity. New telescopes will map cosmic structure in ever finer detail. New theoretical frameworks might suggest entirely new places to look or new types of particles to search for. We might finally detect dark matter directly, identifying the particles that make up 85% of all matter. Or we might continue to narrow down what it isn't, pushing the remaining possibilities into ever smaller corners of theoretical space. Either way, the search continues. Researchers will descend into underground laboratories, run experiments for years without detecting anything, analyze data looking for signals in the noise, build theoretical models, and test them against observations. It's patient work, requiring dedication that spans entire careers, sometimes entire lifetimes. And somewhere in that patient accumulation of knowledge, in that stubborn refusal to give up on difficult questions, in that willingness to spend decades searching for something that might remain forever elusive, there's something deeply human. We are creatures who wonder about our place in the cosmos, who ask questions about how things work and why they are the way they are, who build increasingly sophisticated tools to explore the boundaries of the knowable. Dark matter represents one of those boundaries. It's close enough that we can detect its effects, can map its distribution, can study its influence on cosmic evolution. But it's far enough beyond our current capabilities that we can't quite grasp it directly, can't quite bring it into the light of full understanding. That boundary will likely shift in the coming years. Perhaps we'll finally detect dark matter particles, or perhaps we'll conclude that modified gravity is the better explanation after all, or perhaps we'll discover something entirely unexpected that reframes the question in ways we haven't imagined. Whatever happens, the boundary between known and unknown will move, as it always has throughout the history of science. But there will always be another boundary beyond that one, another question waiting to be asked, another mystery beckoning from just past the edge of our understanding. This is the nature of knowledge. The more we learn, the more we realize how much we don't know. Each answer opens new questions. Each discovery reveals new puzzles. Dark matter is just one of those puzzles, though an important one. It's woven into the structure of the universe, essential to how galaxies form and evolve, crucial to understanding cosmic history. But it's not the only mystery. Dark energy, quantum gravity, the nature of consciousness, the origin of life. Each of these represents its own frontier, its own boundary between known and unknown. And that's okay. That's more than okay. It means we live in a universe that still has room for wonder, still offers opportunities for discovery, still holds secrets waiting to be revealed. That invisible scaffolding of dark matter, holding everything together while remaining hidden from direct view, is a reminder that reality is larger than our ability to perceive it, richer than our theories can fully capture, more mysterious than our mathematics can completely describe. So rest easy tonight, knowing that you live in a universe mostly made of mystery, that the galaxies wheeling overhead are held together by invisible hands, that the cosmic web connecting one side of the universe to the other is woven from something we've never touched, that even in an age of remarkable scientific achievement, profound questions remain unanswered, waiting for future generations to explore. The dark matter is still there, as it has been for billions of years, patient and invisible, holding the cosmos together. And somewhere, in underground laboratories and mountaintop observatories, in computer simulations and theoretical calculations, scientists continue their patient search, adding to our understanding one measurement at a time, one experiment at a time, one carefully constructed theory at a time. The universe doesn't rush to reveal its secrets. It unfolds on its own timeline, indifferent to our curiosity, but somehow accommodating it all the same. And in that slow unfolding, in that patient revelation of hidden truths, there's a rhythm that matches the gentle drift towards sleep, mysterious, inevitable, and somehow deeply right. Good night, fellow traveller through the dark matter universe. May your dreams be filled with invisible scaffolding and cosmic webs, with particles too elusive to catch and mysteries too profound to solve, with the quiet knowledge that the universe is stranger and more wonderful than we yet understand, and that tomorrow the search continues. Clear skies and gentle starlight, the Sleepy Astronomer.